All right, so as a reminder, the homework assignment is due on Tuesday, and we're going to be continuing to talk about a few things related to the NRCS rainfall runoff model today. So curve numbers are affected by the antecedent moisture condition, or antecedent moisture class. And let's say that under normal conditions you'd have a certain curve number. You know, in the quiz we just took, for an average moisture conditions we might have 65. When you're given the curve number for a watershed, the convention is for that to be moisture condition 2. 2 is kind of thought of as typical most of the time, and what it means is that in the last 5 days during dormant season there would be 0.5 to 1.1 inches, or during the growing season 1.4 to 2.1 inches. Now that may vary from place to place, because let's say a really arid region like Phoenix. So, I mean, the types of curve numbers you're going to get for a place like Phoenix, they're not going to be based on the expectation that you had this much precipitation. These guidelines of the antecedent rainfall, I think, are probably targeted more towards the eastern part of the United States where we live, and so there's probably some special applications in drier regions where this wouldn't apply in converting the curve numbers. But for our purposes in this area, if we wanted to know how the curve number is going to change under dry conditions, so antecedent moisture class 1, then you can see there's an empirical conversion here where you're going to come up with some new curve number based on the previous curve number and some adjustment factors. So just to get a feel for how radically those adjustment factors can actually affect the curve number, let's say that initially we had a condition where the curve number was 75 under type 2 conditions. So this is a residential quarter-acre lot on Class B soil. And if we go to the table and look that up, then it'll be 75. So let's find out, you know, if we're starting with 75, how wide can that range go under the dry conditions? So if there's been no rainfall in the past 5 days, or if in July, which is during the growing season, then it's been 3 inches of rain in the past 5 days. So in other words, calculate the curve number under condition 1 and under condition 3 to find out, when you're starting with 75, how high and how low it can go based on the previous rainfall. All right, so if we're looking at how the curve numbers are affected by previous moisture condition, if it's been really dry, then what would start off under normal conditions as a 75 curve number is going to go all the way down to 56. And if it's been really wet, then it could be as high as 87. So is that about what everybody else got? So let's look at the implications of that. You know, with the quiz example of what if we had a storm where the precipitation depth was, if we have a P of 3.75 inches, because this might be deceptive. You think, 87 is only a little bit higher than 56. So maybe it being wet isn't going to contribute to that much additional precipitation. But if we actually find out what's the precipitation excess in both cases, so if we have on the one hand the 56, so I'll have to get out my calculator here. You follow along if you want to double check my math, always good to make sure. All right, so S will be 7.86, and so then the precipitation excess, 3.75 minus 0.2 times 3.75, all of that squared, precipitation 3.75 plus 0.8 times S. Oh, no, 3.75 isn't. S is 7.86. All right. Okay, so the precipitation excess for the curve number of 56, let's see. Okay, so the precipitation excess will be 0.47 inches if we have the precipitation depth is 3.75 and the curve number of 56. Anybody else get this same 0.47? All right, so that's with the curve number 56. So if we change that, what if it is the curve number of 87? So then that's going to change the storage depth. It's going to decrease the storage depth to only 1.49 inches from 7.86. So then that changes the S here. Okay, so for the curve number of 87, then I get the P sub E is going to be 2.41 inches. Let me double check that. That's just my first time through. 3.75. You got that too? All right, well, we probably didn't make the same mistake then. So that's a huge difference, right? It illustrates that, good, yeah. You can't just look at the relatively small difference in curve number and think, oh, it's only going to be, if the curve number decreased by 20%, it's not going to be necessarily a 20% change in the precipitation excess. It's going to be a lot more. So this illustrates that fact, that these antecedent moisture conditions are really important because it makes big changes in the curve number, which leads to huge changes in the rainfall excess. A watershed that, 3.75 inches, that's a lot of rainfall. And so a watershed that barely would have any runoff at all if it had previously been dry, or the majority of that precipitation will turn into precipitation excess if it's been rainy in the 5 days beforehand. Any questions about antecedent moisture class? Yeah.
So on those tables we're looking at for the hydraulic soil groups?
Yeah. These are all type 2.
These are all type 2?
Yeah. So all these values are assuming that kind of middle moisture condition. And if your design condition says, let's find out what's the runoff going to be if it had been a big storm after a small storm that wet everything down, then you'd have to convert this into adjusted curve numbers for that second condition. Good question. All right, so what we can do is come up with weighted curve numbers for watersheds. Just simply by a simple weighted average. So if we have a certain watershed where we've got 40% of the land use with a certain soil group, and we can look up the curve number for it, then you can just come up with a weighted average of the curve numbers. And so we've already been through the NRCS equation a couple of times today. I won't ask you to punch in the numbers for this, but I will show you the solution to that, where all we're doing is just saying 40% of the watershed is one curve number, 25% is another, 20% is a certain, and so we come up with an average overall weighted curve number for the watershed, and then put that into the NRCS method to find out what fraction of a precipitation depth will be as rainfall excess. So it's simple. What's a little bit less simple, though, is when we have impervious area in a watershed. And so I'm going to show you a couple of different cases of where pervious area is connected to impervious area. And remember, impervious are sections like rooftops or concrete or asphalt. And so in this first condition, what we have is a connection between the outlet and the impervious area. So what that means is that this impervious, we can think of it as pavement, for example. The pavement is directly connected to the outlet. The outlet could be maybe a catch basin where all of this flow is concentrating towards. But this pervious area is a section that maybe is grass with a certain curve number. And so in the grassy zone, some of the water is going to be infiltrating down into the soil. Some of the water is going to be running off. And the runoff portion is going to go here to these impervious areas. And so we can look up a composite curve number using a table like this, or you can just do the same method that we did before, where it's a weighted average of the curve numbers. But in this case, if we had 7 acres of grass and 3 acres of pavement, then the connected impervious area, the weighted average would look like 3 acres of 98. So it's a simple weighted average as before. So 3 acres of 98 curve number plus 7 acres of a 60 curve number. And then overall there are 10 acres, so we divide it by 10, and it turns out to 71.4 is the composite curve number. And so the way that we could use this nomograph, if we wanted to use that approach instead, is that the pervious area, it has a curve number of 60. And so we start with the pervious CN curve of 60. So they're saying, okay, so we've got this curve of 60, and that pervious represents a certain percentage of the area. And the impervious area, so this large asphalt section, is 70%. So if we go up to the 70% and the intersection of the pervious CN, and then we follow it, let's see, connected impervious, 70%. Well, it's saying, though, the connected impervious area, which is, 3 acres. Oh, okay, I got the percentages wrong. You're right, yeah, so 30%, thank you. So 30% up to the curve of 60, and then over, it's approximately that same 71.4, 72. So this is just a way of doing the weighted average pretty easily. So nothing special about when the impervious area is directly connected to the outlet. What is a little bit more tricky, though, is when you have the asphalt or the impervious area that's not directly connected. Now look at this figure and try and think, why would this be different than the previous case? It's still the same 3 acres of asphalt. Here we've got 3 acres of asphalt, 7 acres of grass. I've just changed the location of it in this illustration. We've got 7 acres of grass still and 3 acres of asphalt. But what's different? Okay, and why does that matter? The impervious areas at the top of the watershed, why does it matter? Why would there be, is this going to change the overall weighted curve number? There's going to be more water going into the pervious area. Okay, all right. So yeah, I think you're headed in the right direction. Your point was that before, the grass only had the water coming out of the sky, right? Now, the grass has the water coming out of the sky, and it's got the water coming off of the asphalt. So what effect do you think that's going to have on the curve number, though? Like what we said in this example, overall for the composite, the curve number should be 72. Do you think that switching it around is going to increase or decrease the curve number? So you're saying decrease. Why would it decrease the curve number?
You'll have more water that seeds the impervious area, so that there's more water that can infiltrate.
All right, good. So if we think about infiltration, the water that's coming off of this asphalt never had any opportunity to infiltrate. I mean, it was directly connected to the outlet, and so whatever fraction runs off is going to make it to the outlet. But we flip it, and the runoff coming off of this upper section of the watershed is going to be going over the grass. And so some of that might infiltrate down into the grass before it gets to the outlet. And that idea is kind of behind some of the new stormwater regulations in Huntington. What they're trying to do is encouraging people to disconnect their roof drains from the stormwater network in the city. In the past, it was customary to have the water that's coming off of your roof go directly into the stormwater network. But now, they're trying to encourage people to, instead of having that direct connection, if you sever the connection and you have the stormwater coming off of the roof go onto the grass in the yard, some of it is still going to make its way into the stormwater network, but some of it's going to infiltrate. And so it's going to decrease the volume, and at the very least, it's going to slow things down. And so, in addition to the runoff amount, think about the timing of having the impervious area directly connected versus having it unconnected. So the timing is going to be delayed, and we already know that a delay reduces the peak as well. In addition to having an absolute decrease in the volume, any kind of a delay is favorable for us. So the way to use this nomograph is a little bit more complicated than it was in the previous one. What we do is we say we want to know the ratio of unconnected impervious to total impervious. Now here, unconnected means it's not touching the outlet. And we have 100% of the overall impervious area is unconnected. So we would use this 1.0 line. And the impervious area in this example is 30% of the overall 10 acres. So 3 out of 10 is 30%. So 30% and 1. And so we'd go over sideways now and find the curve number for the pervious area. And ours was 60. And then we would follow it down to find that it's about 65 is going to be the composite curve number. So again, the ratio of unconnected to total was 1 because all of the 3 acres is not touching the outlet. And 30% is the total impervious area. So this is the point of interest. And if we go over sideways, and we run into the curve number for the pervious, which is 60, and then go down, then it's right in the middle between 60 and 70. So our composite curve number would be 65. All right, so I want you to try that, try using that nomograph on this next figure here. So on this next figure, you can see some of the impervious is connected, some of it is unconnected. So I've got the answer here of 68, but double check to see if that's accurate. if you get the same thing as the composite curve number. It's easiest if you've got the notes printed out and you can draw right on it. Otherwise, you're kind of using your finger to trace it. All right, so here, 50% of the area is unconnected. So 1.5 out of 3 acres overall is unconnected. So we're going to use this 0.5. The impervious is still 30% of the total area, though. So, you know, if we consider this horizontal axis, we're all the way at the right. And so it's the intersection of 30% impervious and 0.5, the ratio is the amount that's unconnected. And so now we're going sideways over at this location until we intercept the curve number of 60. So there's the 60 curve number and down. And so I said that's about 68. We look at where that line right there intersects the horizontal axis, it's about 68. So this is something that most watershed models wouldn't directly account for if it's automatically computing the curve number. You know, in class last time I said that GIS software can overlay land use and soil type and kind of automatically calculate a composite curve number for you. And it does that according to just kind of a simple average. And it wouldn't take something like this into account, like if you had a cluster of high curve number area close to the watershed outlet versus far away from the outlet. And so you'd need to make manual adjustments yourself if there was something like that. If there was a location where you had you know, particularly high or particularly low concentration of curve number, then you may need to take these factors into account and make subtle shifts to the curve number. Any questions about changes to the curve number? Yeah, in this third example, we've got the unconnected impervious is 1.5 out of the total impervious, and so 50% it would be, you know, this curve that we'd use. Does that make sense? Think about how much impervious do we have overall. There's this 1.5 and this 1.5, so in total there's 3. Yeah, right. Yeah, the denominator over here is the total impervious. So it would be the 3 acres, and then the unconnected would be 1.5 out of the 3 acres. Yeah. All right, so we've got about 20 minutes. We can try and make some more progress on